Dr. Co-coordinator of this one week Aicte at an online FDP. I welcome you all again in our FDP, and we are about to start our next session, sixth session of schedule today. Today's expert is Dr. Tausif Diwan from IIIT Nagpur. Let me take a moment to introduce our speaker, Dr. Tausif Diwan sir. Dr. Tausif Diwan received his MTech in Computer Science and Engineering and PhD in Parallel Computing from Department of Computer Science and Engineering, Visvesvaraya National Institute of Technology, Nagpur, which is known as VNIT, in 2011 and 2017 respectively. Since July 2019, he has been associated with the Department of Computer Science and Engineering at Indian Institute of Information Technology, IIIT, Nagpur, as an assistant professor, and currently working as head of the department. His research area includes parallel computing, machine learning, and deep learning. He has published several research papers in various international conferences and reputed journals. An Australian patent title and IoT-based smart food cold chain transportation system is also granted to his account. He is having association and collaboration with several industries. He is NVIDIA certified DLI instructor for the foundation of deep learning and building transformer-based natural language processing application, which includes several courses, and he secured Platinum Award as a DLI instructor from NVIDIA in the year 2022. I hope he might have joined the meeting. Sir, are you there? Tausif sir?
Hello. Yes, sir. I am here.
So now I, without any delay, I hand over the session to Dr. Tausif Diwan sir. Tausif sir, please take over the session. Thank you.
Thank you, sir. I hope that screen is visible.
Yes, sir.
Okay, so good evening, everyone.
Good evening, sir.
Yeah. Thank you, sir, for the nice introduction. So, yeah, in this today's session, we will be covering deep learning, and in the next, I think that is tomorrow's session, we will be continuing deep learning in healthcare. So, I'm having two sessions. Today, we will be focusing on deep learning only. In today's session, I will try to cover some of the important stuff of deep learning, such as some of the basic concept. In addition to this basic concept, our main focus would be on convolutional neural networks, in which we will study convolutional neural networks in detail, like how this CNN actually works, what are the various architectural layers of CNN, etc. And then in tomorrow's session, we will be looking at the applications of CNN or the utilizations of CNN in various healthcare problems. Before jumping to deep learning, let's quickly summarize the machine learning categorization based on what we are having categorical data or continuous prediction, and what we are having, whether the data that is provided to us is a labeled data or unlabeled data. So in supervised scenario, we are provided with labeled data. For example, one image is given to us, and we also know the label of that particular image. And in unsupervised, we are provided with unlabeled data. In machine learning, we need to predict something. What we are predicting is continuous, or what we are predicting categorical. It depends on the application to application. So based on this classification, we are having these four categorization. One is supervised, and our prediction is continuous. Second one is unsupervised, and once again our prediction is continuous. Then third one is supervised categorical, and then last one is unsupervised categorical. So mostly we can see this classification problem. We would be focusing much on the classification problem. Standard algorithms are there which comes under in each of these categories. For example, in classification, K nearest neighbor, logistic regression, neo bias, support vector machines, all these algorithms comes under the category of classification. So this is just the broad overview. Categorization into two parts, supervised, unsupervised. Supervised is divided into two parts, classification, regression, and unsupervised is divided into two parts, clustering and association, on which we are not focusing much. Okay. This is just a plain architecture of a neural networks. Here we can see it is a very simple neural networks in which various layers are there. The very first layer is known as input layer, and after that another layer is there. Then these two layers are known as hidden layer, and lastly this is the output layer. This is plain neural networks. This is an example of fully connected or dense neural networks. How can we define this fully connected or dense neural networks? One neuron in a layer is connected to all the neurons of the previous layer. If one neuron is connected to all the neurons of the previous layer, then this type of architecture is known as fully connected or dense neural networks. Here we will try to understand some of the examples, and then we will jump to deep learning. So this is the problem, which is nothing but handwritten digit recognition. For example, handwritten digits are provided in the form of images to us. So this can be handwritten digit 0, this can be handwritten digit 1, 2, 3, 4, 5, up to handwritten digit 9. So based on the input image which we are provided with, we need to just determine, or we need to predict which handwritten digit is this. So we can just consider this, or we will try to imagine this entire structure in terms of a neural network. So this is my input. It is nothing but, suppose you may imagine that 28 by 28 grayscale input is there. 28 by 28 is nothing but total 784 values are there in terms of pixel values. So these are my input, which is nothing but the 784 neurons. We are having one hidden layer. We can just put some of the neurons in the hidden layer, and lastly this is the classification layer, final outcome layer. In outcome layer, we will try to predict the probability, like what is the probability that input image is handwritten digit 0. What is the probability that input digit which is provided to us, which is handwritten digit 1, and such that summation of all this probability is equal to 1. And we will identify which probability is maximum, and we will go with that probability. So this is all about the structure. Now here we will try to increase the layers in the neural networks. So this layer, it is known as multi-layered neural networks. In this previous stuff, only a single layer is there as hidden layer. Here we can see 3 layers are there, other than input and output layer. This is again the same example of fully connected or dense neural network. One neuron is connected to all the neurons of the previous layer. Now we will see from where this deep learning is coming into picture. So for this, we will take once again one example in which, suppose just let us say that this is the problem that we need to sort. One input image is provided to us. We need to just identify which this input image is a face image or not a face image. Okay, so you may imagine that this is the classification problem. We just need to identify whether the input image is a face image or not a face image. Okay, now we cannot directly say that this input image is a face image. First of all, we should know that what are the various characteristics or features of a face. For example, if you want to say that okay, this is the face image, then these are the characteristics. The first one be this. There should be an eye in the top left. Then second feature we can say that eye in the top right. Then nose in the middle, mouth at the bottom, hair on the top. Okay, these are some of the features. If the answer of each of these features is yes, then on the basis of these we can conclude that okay, the image which is provided to us is a face image. And what is the input? Input is this, which is provided in the left hand side. Okay, this input is given to us in the form of pixel values, and this is our hidden layer. If we imagine that entire structure in terms of a neural network, so this will become my input layer, this will become my hidden layer, and this will become my last layer. So it's a 3-layer neural network. This one is input, and this is hidden layer. So you may imagine that in hidden layer 5 neurons are there. This is the first neuron which is responsible for detection of an eye in the top left. This is my second neuron which is responsible for detection of an eye in the top right. Third neuron responsible for detection of nose in the middle. Fourth neuron which is responsible for detection of mouth at the bottom, and likewise. Now this is 3-layer neural networks. Now just focus upon the first subproblem. This was the problem. Is this a face? And these are all subproblems of this. Okay. Now just imagine that this is the first subproblem. What is that first subproblem? Eye in the top left. Now we cannot also directly identify that this particular part is an eye. We cannot directly say that. We should once again divide this subproblem into several subproblems. Now you just imagine that what could be the features. Based upon that, we can say that this is the eye in the top left. Like what could be the features that on that basis we can say that there is an eye in the top right. Okay, so there should be some features of the eye. Now see, this was the subproblem, eye in the top left. What should be the features of eye? There should be some eyebrow, there should be some eyelashes, and there should be some iris. Okay. Now, based upon these three, we can conclude that, okay, this is the eye in the top left side. Fine. Come here. This was the subproblem. This subproblem is divided into several subproblems. This subproblem, second subproblem, is once again divided into several subproblems. Third, fourth, fifth. All these subproblems are divided into several subproblems. Now, when one subproblem is recursively decomposed into several subproblems, this process is known as recursive decomposition. This process is known as recursive decomposition. So, you may imagine that subproblems are there, subproblems are divided into several subproblems. In terms of neural network, if we want to imagine that entire stuff, what is happening over here, this is divided into 3 neurons. This is divided into 3 more subproblems. Each subproblem corresponding to 1 neuron. Ultimately, what is happening? 3-layer neural network is getting transformed into 4-layer neural networks. 3-layer neural networks is getting transformed into 4-layer neural networks. This process is continued. For example, now we are just interested in finding the eyebrow. Now, this eyebrow should be once again decomposed into several subproblems. Okay, this process gets on continuing. Okay. Now see here, it is not 3 or 4 layers in a neural networks. You just imagine that it is 100 to 200 layers are there in a neural network, and that's why there is a intuition of deep learning. The meaning of deep in deep learning is nothing but the number of layers in the neural networks. That's why we are calling this as a deep learning. Fine. At any point of time, if you are having any query, then feel free to interrupt me. We will have a discussion and then we will move ahead. Then there are some types of neural networks. Broadly, we can categorize this into two parts. One is that feed-forward neural network, and second one is recurrent neural networks. These are the broader classification of a neural network. In feed-forward, the basic speciality of neural network is that here no loop is there, but in recurrent neural network, once loop is added in the form of feedback. Now, where this deep learning is coming in the context of AI and machine learning. So we will try to understand this with the help of this Venn diagram. AI is nothing but the broader picture. It includes the program that can sense, reason, act, and adapt. Okay. Machine learning is a subset of AI. We need to introduce much more data. Here, algorithms are there that perform. Their performance can improve as they are exposed to more data over time. However, deep learning is once again a subset of machine learning. When more data is there, then we can go with deep learning. So the only thing that should be noticed over here, when we are moving from AI to ML and when we are moving from ML to DL, the size of the data is getting increased. So can we conclude that we should go with deep learning only when we are having ample amount of data? Why deep learning is getting so much popular? Because of these three reasons. First, huge amount of generated data nowadays. See, previously data was very limited, but nowadays enough amount of data that is generated day by day. For example, if we take an example of social networking website, for example, Twitter, LinkedIn, etc. See how many posts that are generated in single day. So this much data is generated nowadays. Previously, we are not having computational capability to a considerable level. We were not having powerful GPUs, we were not having powerful workstation, but this is not the scenario nowadays. Today we are having powerful GPUs, larger workstation to process the huge amount of generated data in the point number one. So data is there to process that data. We are having computational capability. And third one is nothing but the success stories of deep learning in various domains. Deep learning is not only performing tremendously good only in computer vision and not in NLP side, but it is performing tremendously good in all these fields, such as we may not imagine that it is performing very good in computational fluid dynamics. It is performing good for wind estimation forecasting, and lot many things are there. Applications are there in which deep learning is performing very good. So if we talk about that enormous amount of data, let us talk about some statistical side. What sort of data that is generated? So just look at that. Some of the example. If we take one data set, MS Coco, here the size of the data set is 19 GB. We can consider one data set. The name of this data set is ImageNet, in which total 1000 categories are there. See, this is nothing but the classification data set. Here, 1000 images are not there, but 1000 categories are there. And size of that data is 180 GB. ImageNet, a larger version of ImageNet in which total 22,000 categories are there. Size of the data set is of few terabytes. And in industry, size of the data is even much larger as compared to this few terabytes and all. Large neural network means what? 100 to 200 layers are there in a neural networks. And if see that if 100 to 200 layers are there in the neural networks, then billions of parameters would be associated with the neural networks. What is the parameter? Parameters are nothing but the connections between the neural networks. Specifically, we can call this as weight and bias of the neural networks are called as parameter. Faster prototyping or training time. Uh, if we are having this much large neural networks in which 100 to 200 layers are there, millions to billions parameters are associated, and we are also having a larger workstation or computational capability, then training time is also reduced, but it is also considerable. So here we can see training time is can be vary from hours to days, and even sometimes it takes some weeks also. This is the plot between data size and the model performance. You need to compare here this red line and this blue line. See here, on x-axis we are plotting this size of the data, on y-axis we are plotting the model performance. So just see here, when the size of the data is very less, just look at this over here, size of the data is very less, then traditional machine learning algorithms such as support vector machine, logistic regression, it perform better as compared to this large neural networks. Okay, see the compare this to performance. Okay, and when we are having very huge data with us, for example, we are at here, then see this is the performance of traditional algorithm and this is the performance of large neural network, that is deep learning. So from these two graphs, we can conclude that deep learning will perform better when we are having enough amount of data, and when we are not having ample amount of data, then we should go with some traditional machine learning algorithms such as logistic regression, support vector machine, etc. It is performing very good in various domains such as digit recognitions, object classification, segmentation, image captioning, gameplay, AI, translation, neural computing, routing, etc. Coming to the models which comes under deep learning, the very popular one which we will explore is nothing but convolutional neural networks. So, and some other stuffs are also there such as recurrent neural networks, the architectural variants of recurrent neural networks such as long short-term memory, gated recurrent unit, deep belief networks are there, then deep autoencoders are there, etc. Now we will start with convolutional neural networks. So first of all, we will define these convolutional neural networks, and then we will go deeper into the convolutional neural networks. This is a deep neural network which is designed for automatic feature extraction and classification. Before the advent of these convolutional neural networks, we were doing this feature engineering manually. We need to decide which features that we should use, which features that we should use. If we are having 100 features, then we need to also identify the important features manually and the other non-important features that we need to discard. All these things where we were doing manually. But when CNN came into picture, then it was automatic feature extractor. See, manual feature engineering, we are not performing anymore. Previously, this CNN was adopted for working with two-dimensional image data, but nowadays it is not the case. It is performing tremendously good for single-dimensional data also and for multi-dimensional data also. Previously, it was designed that, or it was suggested that it should perform good only with image data or visual modality. But this is also not the case. It is it perform better with some of the state-of-the-art model in comparison with CNN for the other modality also. For example, the audio modality, then textual modality. Okay. Uh, if we can compare this CNN with the other fully connected networks, so we know that what is fully connected neural networks. In fully connected neural network, one neuron is connected to all the neurons of the previous layer. Okay, but in CNN, one neuron is connected to a local region of the previous layer. Now, just imagine that when one neuron is connected only to a local region of the previous layer, then fewer connection would be there in comparison with the fully connected neural networks. And when we are having lesser parameters, lesser connections in CNN, then the model will be lightweight as compared to fully connected neural networks. If the model will be lighter, then it is easy to train that particular model because it has fewer parameters. So conclusion is that in CNN we are having fewer parameters, so model training is easy and faster also. Application domain, it is working tremendously good in computer vision. Various problems of computer vision such as classification, recognition, object detection, performing tremendously good in NLP side. For example, if we take an example of sentiment analysis, such as for example, one input is given to us. We are interested in finding that which sentiment is associated with that input. For example, the sentence is there, I like the movie. So we need to just figure it out which sentiment is associated, whether positive sentiment, negative sentiment, or neutral sentiment is associated. Then a similar problem to sentiment analysis is the second one, which is nothing but emotion detection. So input is given to us. We need to identify the associated emotion with that particular input. Emotions can be sorrow, joy, fear, disgust. Okay, any emotions that we need to extract. One more interesting problem related to sentiment analysis and emotion detection is nothing but sarcasm detection. Sarcasm detection is nothing but inherent negativity is associated with the input. For example, if we say that I like the movie so much that I left in the interval itself. Okay, so by looking at this particular sentence, it seems positive. It seems positive, but inherent negativity in terms of taunt or in terms of bitterness is associated with that input. That is nothing but sarcasm. Now, this type of input is given to us, and we need to just figure it out whether the sentence is sarcastic or non-sarcastic. Now, this is the generic architecture or intuition of CNN. First of all, we will see this generic stuff, and then we will move to the architectural part. So what we need to do here, input image is provided to us. We need to just classify whether the input image is a car image, whether the input image is a truck image, whether the input image is a van image, or likewise bicycle and all these things. The entire pipeline is divided into two parts. One is that feature extraction, and second one is the classification. We can see here feature extraction is done through convolutional layer, and after that fully connected layers are applied over here. This is nothing but the classification part. Here we had seen that what is convolutional neural networks and how it is different than fully connected neural networks. In CNN, one neuron, just look at this. Here one neuron is connected only to a local region of the previous layer. Just see here. This is nothing but the local region to which this neuron is connected. These connections are known as filter. This filter is revolving over the input and extracting the features. This is nothing but the convolution operation. We will see the convolution operation in detail what is happening, but this is just a broader intuition of this. Then after this convolution, we are having another layer which is nothing but pooling or max pooling or downsampling, which extract the important features and ignore the non-important features. See here, this is the pooling layer. Generally, pooling layer is applied along with this convolution operation. Convolution followed by pooling is called as convolutional layer broadly. Similarly, we are having multiple such convolutional layers. So this entire pipeline of successive convolutional layers are known as feature extraction through convolutional layers. Once all these features are extracted, then these extracted features are given to the fully connected neural networks. Just look at this, fully connected neural networks. Then several fully connected networks are there, and finally this is the classification layer. We will see one more example. This is the second example in which we are interested in recognizing the handwritten digit. So see here, this input image is provided to us. This is my input image, this one. And on this input image, it is the size of 28, 28, 1. For example, 28 is the width, 28 is the height, and number of channels is nothing but 1. We may imagine that it is a grayscale input. That's why only single channel is there. See, if it would be a colored input, then 3 channels would be there, RGB. then this would be 28, 28, 3, but here it is 28, 28, 1 only. On this input, so very first thing we need to apply convolutional layer. So here we are applying 5 cross 5 filter. See here, this is my 5 cross 5 filter that we are applying on this. Filter is revolving over the input and then it is generating this feature map. We are applying multiple convolutional layers. So see here, we are applying N1 filter over here. This is the outcome of applying these filters. And after that, this 2+2 max pooling is there, which is nothing but 24, 24. So this 24, 24 is getting converted into 12 cross 12 and same N1 channels are there. This is nothing but my convolution. First convolutional layer, then second convolutional layers are there, then fully connected layers are there, and finally this is the classification layer. This is once again the broader overview. Now, by looking at these two examples, this is first one and this is the second one, we can see the generic architecture. What is happening in generic architecture? First of all, input is there. On this input, we are having convolutional layer. This is the first convolutional layer. After that, pooling layers are there. Then another convolutional layer. Then once again, pooling layers are there. How can we write this generically? Input is there. After that, convolutional layers are there. In convolutional layers, neurons are there. The neurons of the convolutional layers are activated with the help of nonlinear activation functions. Generally, we use the nonlinear activation functions for activating the neurons. There can be any nonlinear activation functions such as sigmoid, ReLU, 10H, etc. So here, for the sake of simplicity, we are using this ReLU as a nonlinear activation function. So see here, convolution is repeated I times. After that, pooling layer is there. So we can see this is pooling, and this pooling layer is optional. We may or we may not use pooling. Now this entire stuff, convolutional followed by pooling, convolutional followed by pooling, this entire stuff is repeated J times. After that, some more fully connected layers are there. Once again, the neurons of fully connected layers are activated using ReLU, which is repeated K times. Once again, some more fully connected layers are there, which are repeated L times. Here, I, J, K, and L. These are simply integers. Okay, these are simply integers. So in this architecture or in this diagram, can we identify the value of I and J? See, the value of I here is 0 and the value of J here is 2. For example, we are not having successive convolutional. For example, convolutional layer 1 followed by convolutional layer 2 followed by convolutional layer 3 without pooling. If it would be the case, then the value of I would be something. But here it is not like that. Convolutional followed by pooling, which is repeated 2 times. Convolutional followed by pooling, and it is repeated 2 times. First one, this is convolutional followed by pooling. Second, convolutional followed by pooling. The value of J here is 2. The first one and then second one, like this. Next, we need to understand the layers of CNN. First one is convolutional layer, second one pooling layer, third one fully connected or dense layer. And in addition to this, we are having some nonlinear activation function, which preferably we use ReLU. Convolutional layer is the very first layer and it is the most important layer in CNN. Ultimately, what is happening? It is the first layer, which is responsible for extracting features from the input. It's a mathematical operation. Filters are there. Filters are applied on the input. We perform element-wise multiplication and then finally results are accumulated over here. We will try to understand this with the help of an animation. Look at this. Okay. So with this animation, we will see what is happening in convolutional operation. One input is there. The size of the input is 5 cross 5. See this matrix. 5 cross 5 is the matrix, which is nothing but our input. On this input, we are applying 3 cross 3 filter. See, this 3 cross 3 filter is revolving over the input. And what it is doing, filter is same, but filter is revolving over the input. First of all, filter is at first position, then it is shifted one position right, then one position right. After that, filter is shifted one position down, like this. And what is happening over here? We are performing element-wise multiplication. After performing element-wise multiplication, we are summing all these values, and then we are generating this very first entry 4. Filter is shifted one position down. Then we are generating this 3. Then once again filter is shifted one position right. Then we are generating this 4. Filter is shifted one position down. Then we are generating this second row. This outcome is known as feature map. This outcome which is generated over here is known as feature map. Now, can we establish some relation between the size of the input, size of the output, and filter size? For example, here the input size is 5 cross 5. Filter size is 3 cross 3. And what is the output size? Output size is once again 3 cross 3. So we will try to formulate one relationship between these. Can we say that can we say that output width is equal to filter width minus, input width minus filter width plus 1? For example, output width is equal to input width. Input width is nothing but 5 minus filter width, which is nothing but 3. 5 minus 3 and plus 1. 5 minus 3 plus 1 is nothing but 3. So output width is 3. Similarly, output height is equal to input height minus filter height plus 1. Okay. So at this point of time, we can say that, okay, this formula is working. We will see one more example over here. This is the convolution operation, but it is not in the animated format. Input image is there. Size of the input image is 7 cross 7. Size of the input image is this 7 cross 7. 7 cross 7 input is there. On this 7 cross 7 input, we are applying this filter. The filter size is 3 cross 3. Okay. And then this 3 cross 3 filter is applied on the input. First of all, this would be applied on this region. Perform element-wise multiplication, and then this 0 is calculated. After that, the same filter is shifted one position right. Filter comes on this position, and then you calculate this one. Likewise, okay. Now just see that whether the formula which we established just now is working or not. Output width is equal to input width. What is the input width over here? Input width is 7. 7 minus filter width is 3. So 7 minus 3 is 4 and plus 1, which is nothing but 5. Okay, fine. It is working. Now, once again, we jump over here. It is nothing but the convolutional layer. Convolutional is the very first layer, which is responsible for extracting features from the input. It's a mathematical operation. Filters are applied on the input. Then you generate that feature map. It computes the output of a neuron, which are connected to a local region, each computing a dot product, specifically element-wise multiplication. And basically what it is doing, it is converting an input volume to an output volume. These are some of the terminologies of convolutional layer. First one, filter, stride. It is also known as receptive fields. All these are same. Filter, kernel, receptive fields, all these are same. In literature, you will find that these terminologies are used interchangeably. Sometimes they call this as filter, sometimes they call this as kernel, sometimes they call this as receptive fields. Filter is fine. Look at this. Filter is 3 cross 3 filter. What is stride? Stride is nothing but by which the filter is getting shifted on the input. For example, here see, filter is shifted by one position. So stride is equal to 1. If the filter would have been shifted by 2 positions, then the stride is 2. Okay. Stride is simple. Stride means position by which the filter is shifted over the input. It can be unit stride if it is shifted by one position. So this is the animation in which filter is shifted by one position. Okay. In this animation, stride is 1, but it can be 2, it can be 3, like this. Third one is nothing but padding. Sometimes we may not find that valid input is there. For example, if the stride is 3, okay, if the stride is 3, so initially the input would be at this position, and then it is shifted by 3 position. So it would come on this. Okay. But here we can see this is not the valid reason because the last column is not there. If this would be the scenario, then we need to pad the boundaries of the input with zeros. Okay, we need to pad the boundaries of input with zero. It is called zero padding. It is called zero padding. So we need to decide whether we should go with padding or we should not go with padding. So there are two options. Then last one is nothing but the number of parameters that we need to calculate. Spatial arrangement, what the shape will be generated, it actually depends on these four parameters. Means here see, what is the shape of the outcome? 3 cross 3. In this, what is the shape of the outcome? It is 5 cross 5. This outcome is dependent on the four things. The very first one is the filter size, which is also known as spatial extent. Okay. Filter size. Filter size decide, it is the most important part by which we can decide what will be the shape of the outcome. Second, depth. In all these animations, see here how many filters we are applying. Here we are applying single filters. But this is not the case always. We can apply multiple filters. We may apply 2 filters, we may apply 20 filters, we may apply 200 filters. Okay. Second most important thing is that how many filters we are applying. Okay. Then third one, slide, by which we slide the filter. It can be unit slide, it can be non-unit slide or anything. The last and the most important part is nothing but zero padding. So here we need to decide whether we are applying padding on the boundaries of zeros. So these are the four things that we need to see. Based upon these four things, we can identify or we can figure it out the shape of the outcome. First one is the filter size. Second one is the depth, number of filters that we are using. Third one is the stride, and the fourth one is zero padding. This is the example of padding. Sometimes filter doesn't fit perfectly with the input. So we are having two options. Either we should consider the region validity. If the region is not valid, then just discard that region, or otherwise we will pad the boundaries of the input with zeros. Okay. This is another animation. Here we can see in this animation we are applying two filters. First input is given to us. Filter is there, this red filter, which is revolving over the input, generating first feature map. Then second green filter is coming into picture. Once again, that green filter is revolving over the input, extracting the second feature map. These feature maps are cascaded in the depth-wise fashion. These feature maps are cascaded in the depth-wise fashion. See here, this is the first feature map, and then second feature map. Question is that why there is a necessity of applying multiple feature maps? Question is that why there is a necessity of applying multiple feature maps? See, one feature map is responsible for detection of some important features. That filter or that receptive field is not utilized for detection of some other important features. For example, in this animation, we can conclude that first filter is used for detection of horizontal edge. Second filter is used for detection of vertical edge. Okay, horizontal edge and vertical edge are the features. Okay, and what this filter would be doing, this filter is revolving over the input and just figure it out on which part of the input horizontal edge or vertical edge is there. If horizontal edge or vertical edge is detected, then it will outcome as 1, otherwise it will outcome as 0. Okay, so multiple filters will be applied. One filter may be applied for detection of horizontal edge, another filter may be applied for detection of vertical edge, third filter may be applied for detection of a circle, fourth filter may be applied for detection of a slanted edge, like this. We are concluding that multiple layers are there in a CNN. So we can divide all these convolutional layers into two parts. First part is nothing but initial convolutional layers, and second part are nothing but later convolutional layers. Initial convolutional layers are responsible for capturing low-level features such as horizontal edge, vertical edge, etc. Later convolutional layers are responsible for capturing the high-level features. For example, P. Initial convolutional layers are responsible for detection of horizontal edge and vertical edge. Okay, horizontal edge and vertical edge, with the combination of horizontal and vertical edge, you can club horizontal and vertical edge to form a square, to form a rectangle, or to form some other shape such as pentagon, etc. Okay, so initial convolutional layers are responsible for capturing low-level features such as horizontal edge and vertical edge, and later convolutional layers are responsible for capturing high-level features. For example, it may be square or anything. This we can try to understand with the help of one very interesting examples. We will see in this book, actually, one very good example is there for initial and later convolutional layers. So let's see whether we can see this example. Okay, see here. This one. See here in this example, what we need to do. So this is the cat image. Ultimately, we need to just identify whether input image is a cat image or it is a dog image. Okay. So here we can see these are the initial convolutional layers. Okay. And these are the later convolutional layers. So here we can see these initial convolutional layers are responsible for capturing low level features. So this slanted edge, this slanted line, this, all these are nothing but the low level features. Okay. By combining these low level features, we are forming this high level features. Okay, and based upon this high level features, okay, we are concluding that okay, this image is a cat image. Okay, so these are the initial convolutional layer responsible for capturing low level features. These are later convolutional layer responsible for capturing high level features. Now we apply filter with the help of that backpropagation or gradient descent algorithm, which with which the model trained. The model aim is that to learn that particular filter. See, initially we don't know the value of that filter. We need to learn that filter. Okay, and this is done with the help of backpropagation or gradient descent algorithm. These are some of the standard filters. For example, if we are interested in determining identity, age, sharpen, blur, etc. So these are the standard filter that we can use. We will try to understand this example of convolution. Okay, if this example is clear to you, then you will understand the CNN working perfectly. The input shape which is provided to us. Okay, so the input shape, what is the shape of input over here? 6 cross 6. See here, the width is 6, height is also 6. Yeah, just imagine that it's a colored input. That's why 3 channels are there. So this is the first channel of input. then this is the second channel of input, and then this is the third channel of input. So total how many input values are provided? 6 multiplied by 6, that is 36. 36 multiplied by 3. These many values are provided as input. In this total picture, how many filters we are applying? We are applying 2 filters. This is the filter 1, okay, and this is the filter 2. What is the observation? Observation is that number of channels in the filter is equal to number of channels in the input. For example, see, this is my first filter. What is the size of this filter? Size of the filter is 3 cross 3. Okay. But see, we need to also look at that on which filter, on which input it is applied. This filter will be applied on this input. And how many channels are there in the input? 3. Okay. So here we can see in this input also 3 channels are there. First channel, second channel, third channel. 3 channels are there in filter, 3 channels are there in input. How will you perform the convolution operation? You just put this on this region to perform element-wise multiplication. So first channel values of the filters are multiplied with first channel values of the input. Second channel of the filter is multiplied by second channel of the input. Third channel of the filter is multiplied by third channel of input. Total how many multiplications would be performed? 9 multiplication corresponding to first channel, 9 multiplication corresponding to second channel, 9 corresponding to third channel. Total 27 multiplications are performed. After performing this 27 multiplication, we sum all this and then we generate this first entry. We generate this first entry over here. Okay. Then this filter is shifted one position right. Filter comes on this position 9 to 5, 6 to 4, 4, 5, 4. Once again, you perform element-wise multiplication. You generate second entry. Filter is shifted one position right. You generate third entry. Filter is shifted one position right. You generate the fourth entry. First row is completed. Then filter is shifted one position down. When filter is shifted one position down, then you generate second row of this. See, this is nothing but the second row. When filter is shifted one position down, one position down. Just look at that, whether the formula is working or not. What was the formula that we established earlier? That output width is equal to input width. What is the input width? 6 minus filter width, that is 3. 6 minus 3 plus 1. So this is nothing but 4 cross 4. See, this is 4 cross 4. This 4 cross 4 is nothing but the result of applying first filter on this input. I am repeating this. This 4 cross 4 outcome is nothing but the result of applying filter 1 on this input. Similarly, this second 4 cross 4 matrix is the result of applying second filter on the same input. This second feature map is nothing but the result of applying second filter on the same input. See, these first feature map, this is the second feature map. These feature maps are cascaded in the depth-wise fashion. What is the final shape of outcome? What is the final shape of outcome? Which is nothing but 4 cross 4 cross 2. See here, final shape of outcome is 4 cross 4 cross 2. Why it is 4 cross 4 cross 2? Because we are applying 2 filters. Because we are applying 2 filters. You remember that final shape of outcome is dependent on the 4 parameters. And which are those 4 parameters? First one was that filter shape. Yeah. First one was that filter size. We are applying 3 cross 3 filter. Second one, number of filters that we are applying. Third one, stride, by which filter is getting shifted on the input. And fourth one is padding. Okay. See, once again, these 4 things are there. Filter size. What is the filter size? 3 cross 3. Second, how many filters we are applying? 2 filters we are applying. Second, third one, stride, by which filter is getting shifted on the input. Filter is shifted by 1 position. So stride is 1. And last one, 0 padding. So are we applying padding to the boundaries of 0? No. Okay. So these are the 4 things. Based upon that, output shape is decided. What is the shape of output? shape of output is 4 cross 4 cross 2. Okay. Now, there were 4 things that we need to understand. First one, convolutional layer, pooling layer. After that, fully connected layers are there, and last one is nothing but the number of parameters that we need to understand. Now, with the same example, we will try to understand the number of parameters. Okay. Now, parameters are nothing but the weight and biases. Okay. Parameters are nothing but weight and biases. For example, see, this is the first parameter. This is the first filter. How many parameters are associated with this? This first 3 cross 3 is the first channel. Total 9 parameters corresponding to first channel. Then second 9 parameters corresponding to second channel. Third 9 parameters corresponding to third channel. Total how many weights would be there? 9 weights for first channel, 9 weights for second channel, 9 weights for third channel. Total 27 weights are there. In addition to these 27 weights, one bias would be associated with one filter. So 27 plus 1, it is nothing but 28 parameters. So 28 parameters are associated with one filter. And how many such filters we are applying? We are applying 2 such filters. Then the total number of parameters would be 28 multiplied by 2, which is nothing but 56. I am repeating this calculation. See, we need to calculate the total number of parameters associated with this. So we need to first identify how many parameters are associated with one filter. Parameters are nothing but weight and biases. So we need to look at one filter. So see this first filter. We just look at that. How many channels are there in the filter 1? Okay. So 9 weights corresponding to first channel, 9 weights corresponding to second channel, 9 weights corresponding to third channel. So total 27 weights are associated. Okay. In addition to this 27 weights, one bias would be associated with every such filter. Okay. So the total number of parameters are nothing but weight plus biases. So 27 weight plus 1 bias. 27 weights plus 1 bias is nothing but 28 parameters. These 28 parameters are associated with one filter. How many such filters we are applying? 2 filters we are applying. That's why the total number of parameters would be 28 multiplied by 2, which is nothing but 56. Look at that output. What is the shape of the output, or what is the depth of the output? Depth of the output is 2. Why depth of the output is 2? Because we are applying 2 filters. If we would have applied 20 filters, then the depth of the output would be 20. Shape of the output would be 4 cross 4 cross 20. Fine. Now, next one is the pooling layer. Pooling layer is the supporting layer of convolutional layers. Pooling layer is responsible for reducing the spatial size of the convolved features. We need to extract the important features for which we are having pooling layer. Okay. So basically, with the help of convolutional layer, we extract features. Now, in these features, some features may be important, some features may not be that much important, for which we are having pooling layer. The task of pooling layer is to capture or to extract the important features and to ignore the non-important features. This is the task of pooling. Okay. There are various kind of pooling, but at this moment, we will try to understand only 2 important pooling. One is that max pooling, and second one is average pooling. Pooling is also known as downsampling. Okay. Intuition is extracting the dominating features. So max pooling returns the maximum value of the region which are considered, and average pooling returns the average of all the values. For example, this is the demonstration of pooling operation. For example, 4 cross 4 input is given to us. On the 4 cross 4 input, if we are applying 2 cross 2 max pool with the stride 2, see here, do not get confused with the stride of pooling and the stride of convolution. See here, filter is not there. Here, stride means only that region of consideration. So see, when we are applying 2 cross 2 max pool, so first 2 cross 2 region is considered 1156. 6 is maximum, it is taken out. Now stride 2 means second region of consideration would be this 2478. 8 is maximum, it is taken out. Remaining entries 247 are discarded. Then next, it is shifted 2 position down, then it will be 3, 2, 1, 2. Okay, then 3 is taken out and rest all entries are discarded. So this is nothing but an example of max pooling. Here we can see the comparative analysis of max pooling and average pooling. See, in max pooling, we take the maximum one and ignore the other entries. But in some of the applications, we are not interested in ignoring the other feature information, because it depends on application to application. In some of the application, we may be interested in maximum one. In some of the application, we may not be interested in maximum one, but we may be interested in all the entries. So if we are interested in all the entries, then we should go with average kind of pooling. But if we are interested in maximum one, then we can go with some max kind of pooling. So the first is nothing but example of max pooling, in which we are taking the maximum one. The second example is nothing but we are taking the average of all these values. By considering all these values, we are not simply discarding the remaining values. So this is the example of average pooling. Third layer was that dense or fully connected layer. We already know that what is the meaning of this line. Dense or fully connected neural networks means one neuron is connected to all the neurons of the previous layer. Here, see, this is another unrolled example in which this is simply unrolled example. For example, see, in this example, 3 channels are there. 3 channels are there in the input, but how many inputs are there? Only single input is there, but in that single input, 3 channels are there. Okay, these are nothing but those 3 channels. So this will become the first channel, input channel number 1. This will become second channel. This will become third channel. On this input, how many filters we are applying? See, do not get confused. We are not applying 3 filters. We are applying single filter over here, but these are different channels of that filter. This will become the first channel of the filter. This will become second channel of the filter. This will become third channel. And why 3 channels are there in the filter? There would be 3 channels. Why? Because 3 channels are there in our input. Number of channels in the input is equal to number of channels in the filter. We are performing element-wise multiplication. So see here, 3 cross 3 is the filter size. 3 cross 3, 9 weights corresponding to first channel, 9 weights corresponding to second channel, 9 weights corresponding to third channel. Total 9 plus 9 plus 9, 27 weights are there. In addition to this 27 weight, we can see one bias is added over here. So 27 plus 1, which is nothing but 28. 28 parameters are there. Filter is shifted. Filter is getting revolved over the input, and then we are generating this final feature map. Okay. Now we come back to that. Here, one more observation you can see. In addition to this filter, in addition to this input, here we can also know that we can also see that zeros are padded to the boundaries of input. See here, zeros are added to the boundaries of input. For example, if padding is equal to 1, then 1 column in the left, 1 column in the right is added over here. What was our previous formula for calculation of outcome, which is nothing but input minus filter width plus 1. Okay, but if padding of 1 is applied, then 1 column in left, 1 column in right is added as zeros. 0 padding is added. Okay, that will effectively become twice P. So see here, previously our formula was this W, which was input width minus filter width plus 1. Okay, here if padding is applied or if padding is not applied, if padding is not applied, then P will become 0. Okay, so this will become 0. Stride is equal to 1, means filter is shifted by 1 position, which is happening in this. Filter is shifted by 1 position, but filter can be shifted by 2 position, but filter can be shifted by 3 position. It depends on stride. So in this example, if padding is not applied, then P will become 0. Stride is 1, then S will become 1. Then the formula will be W minus F plus 1, which is nothing but the same formula which we established, input width minus filter width plus 1. Okay, but this is not the generic formula. If we are applying padding, if P is equal to 1, then effectively it will add twice P in the width, because one column in left, one column in right, one column in one row in up and one row in down will be added as zeros, which is called zero padding. That's why it will become twice P. So effective width will become W plus twice P. W plus twice P divided by S. If it is 1, then no issue. If it is non-unit stride, then it can be divided by S, and ultimately we need to add plus 1 over here. So this is the generic formula. We will try to understand this example to understand the number of parameters calculation. In this example, input is there. The shape of the input is 32, 32, 3. 32, 32, 3 means 32 is the width, 32 is the height, and 3 channels are there in the input. Total, how many values would be there? 32 multiplied by 32, 32 multiplied by 32 multiplied by 3. So this is nothing but 3072. At this moment, we are not applied any parameters. We are not applied any filter. So here number of parameters is 0. On this input, we are applying 5x5 filter. So on 32, 32, we are applying 5x5 filter. Stride is 1. So just look at that formula. P is 0 and S is 1. Okay. So this will become W minus F plus 1. So W is 32, F is 5, 32 minus 5 plus 1. This will become 28, 28. Okay. So from this 32, 32, it will becoming 28, 28 after applying this 5x5 filter, which is perfectly fine. Can you identify or can you say that from where this 8 is coming into picture? This 8 is coming into picture. This 8 is nothing but the total number of filters that we are applying. Look at this. This one. This is 4 cross 4 cross 2. And why 2? Because we are applying 2 filters. If we are applying 3 filters, then this would be 4 cross 4 cross 3. If we would apply 10 filters, then this would be 4 cross 4 cross 10. Okay. Here, in this example, shape is generated as 28, 28, 8. What would be this 8? This 8 is nothing but the number of filters that we are applying. Okay. This activation size is simply multiplication of this 28 multiplied by 28 multiplied by 8. So these many values would be there. Now, number of parameters that we need to calculate. This is interesting. Number of parameters. If we are applying 5x5 filter, then we need to see on which input we are applying. On which input we are applying this 5x5 filter is applied on this input 32, 32. On this 32, 32, how many channels are there? 3 channels are there. We know that number of channels in the filter is equal to number of channels in the input. 5x5 filter means how many weights? 5x5, 25 weights are there. 25 weights corresponding to first channel, 25 weights corresponding to second channel, 25 weights corresponding to third channel. See, this 5x5 filter is applied on this input. And on this, in this input, 3 channels are there. So, how many filters, how many channels would be there in this filter? 3 channels. First 25 weights corresponding to first channel, second 25 weights corresponding to second channel, third 25 weights corresponding to third channel. Total 25 plus 25 plus 25, 75 weights would be there. In addition to this 75 weights, one bias would be there. So this total number of parameters associated with single filter will become 75 weights plus 1 bias is nothing but 76 parameters are associated with single filter. Now, how many filters we are applying in this operation? We are applying 8 such filters. So this will become 76 multiplied by 8. And if you perform this multiplication, 76 multiplied by 8, this will be 608. On this input, 28, 28, we are applying pooling. 2 cross 2 max pool with a stride 2. So 28, 28 is getting converted into 14, 14. Okay. And number of channels would remain unchanged. So total how many values are remaining? 14 multiplied by 14 multiplied by 8. So it is nothing but 1568. And in pooling operation, no parameters are associated. Now, this is the final shape, 14, 14, 8. On this 14, 14, 8, once again, we are applying 5x5 filter. See, this is convolution 1, this is convolution 2. In this convolution 2, once again, we are applying 5x5 filter. This 5x5 filter is applied on 14, 14. So this will become 14 minus 5 plus 1. So this will be 10, 10. From where this 16 would have been coming into picture? 16 is nothing but the number of filters that we are applying. Finally, how many values are there? 10 multiplied by 10 multiplied by 16 is nothing but 1600. 5 cross 5 filter is applied on which volume? This 5 cross 5 filter is applied on this volume. 14, 14, 8. In this 14, 14, 8, how many channels would be there? 8 channels would be there. If we are applying 5 cross 5 filter on an input which is having 8 channels, now we need to identify the number of parameters. So 5 cross 5, 25 weights corresponding to one channel. Number of channels in the input is equal to number of channels in the filter. How many channels would be there in the filter? 8. Because on which input we are applying? We are applying on this input, 14, 14, 8. On this 14, 14, 8, 8 channels are there. 5 cross 5, 25 weights corresponding to first channel, 25 weights corresponding to second, third, fourth, fifth, sixth, seventh, and eighth. Total how many channels are there? 8. 25 multiplied by 8 is nothing but 200. 200 weights are associated. 200 weights are associated. In addition to this 200 weight, one bias would be there. So this will become 200 weights plus one bias. 200 weights plus one bias. This will be 201 parameters. 201 parameters associated with single filter. And how many filters we are applying? We are applying 16 such filters. So we need to perform this multiplication. 201 multiplied by 16 is nothing but 3216. These many parameters would be associated. Once again, we are applying 2 cross 2 max pool on 10, 10. 10, 10 will convert it into 5, 5. 16 will remain unchanged. So this is the pooling. After that, fully connected layers are there. This fully connected layer in which 120 neurons are there. So these 120 neurons, each of these 120 neurons is connected to all the previous layer neurons. And how many values are there in the previous layer? 5 multiplied by 5 multiplied by 16. So this will be 400. So this 120 neurons are connected in a fully connected fashion to this 400 values. I am repeating this. This 120 neurons are connected to this 400 neurons in a fully connected fashion. Each of these 120 neurons is connected to all the neurons of this 400. Fine. How many connections would be there? 120 multiplied by 400. 120 multiplied by this 400, which will become 48,000. 48,000. Okay. Now this is input 400. This is output 120. Okay. We just imagine that these 120 neurons, with each of these 120 neurons, one bias would be associated. We need to identify the total number of parameters. How many connections would be there in terms of weights? 120 multiplied by 400, this will become 48,000. And how many bias would be there? 120 biases would be there. One bias corresponding to one neuron. How many neurons are there? 120. So 48,000 plus 120, which will become 48,120. After that, one more fully connected layers, which is nothing but 84 neurons. 84 neurons are connected to these 120 neurons in a fully connected fashion. Total number of weights would be 84 multiplied by 120 plus 84 bias. So this will become 10164. After that, this is last layer, classification layer, in which 10 neurons are there. These 10 neurons are connected to these 84 neurons in a fully connected fashion. So 10 multiplied by 84, these many weights would be there, 840. Plus this 10 bias would be there, 840 weights plus 10 bias, which will become 850. So these are nothing but the number of parameters. Now we will try to understand this generalization of convolution operation, and then we will stop. And after that, we will take some queries of the participant. Okay. Then see, first generalization, we are having this input W1, H1, D1. W1 is the width of the input, H1 is the height of the input, and D1 is the depth, means number of channels in the input. Okay. On this input, we are applying filters. We need to also figure it out how many filters we are applying, which is nothing but indicated by K. Spatial extent, the filter size, F cross F. stride S, and the zero padding. We should know these four things. How many filters we are applying, what is the size of the filter, what is the stride, and is there any zero padding. Based upon that, we generate one outcome volume. The shape of this outcome volume is W2, H2, and D2. Okay, W2 is calculated like this: W1 minus F plus twice P divided by S plus 1. Similarly, H2 is calculated H1 minus F plus twice P divided by S plus 1. Okay, these are the simply normal formula that we have studied. D2 is equal to K. What this indicate? D2 is equal to K. What is D2? D1 is nothing but depth of the input, and D2 is the depth of the output. D1 is nothing but number of channels in the input. D2 is nothing but number of channels in the output. How many channels would be there in the output? It completely depends on the number of filters that you are applying. If you are applying 2 filters, then the depth of the output is 2. If you are applying 20 filters, then the depth of the output is 20. How many filters you are applying? You are applying K filters, then the depth of the output D2 will become K. This is fine. Now 2 more points that we need to understand. Last point and the second last point. Second last point. With parameter sharing, it introduces F cross D1 weights per filter for a total of F cross D1 multiplied by K weights and K biases. Okay, this is perfectly fine. What is the filter size? Filter size is F cross F. We need to see on which input we are applying this filter. We are applying this F cross F filter on this input, W1, H1, D1. D1 is the number of channels in the input. Fine. Now we need to find out how many weights and how many biases would be there. See, F cross D1. D1 is this depth. Okay. So F cross D1, these many weights would be there. Okay. Corresponding to one filter. And how many filters we are applying? We are applying K filters. Then F cross D1 cross K. These many weights would be there. We know that one bias would be associated with one filter. How many biases would be there? K biases, because we are applying K filters. Total number of parameters would be F cross D1 cross K plus K. We can take K as common. If we take K common, then it will be F cross D1 plus 1. If we take K common, then it is F cross D1 plus K. The same thing that we were doing over here. See, when we are applying 5 cross 5 filter, then this is 5 cross 5 multiplied by 8. 5 cross 5 multiplied by 8. Fine. So which is nothing but 5 cross D1. Okay. After that, we are adding plus 1 because one bias is associated with one filter. Okay. And after that, we are applying 16 such filter. So this will become 5 cross 5 multiplied by 8, which is nothing but 200. 200 plus 1, that will become 201. 201 is multiplied by 16. Same thing is happening over here. 5 cross 5, this F cross F multiplied by this D1. What is this D1 over here? This is 8. Okay. And then plus 1. One bias is associated. So this will become 5 cross 5 multiplied by 8, which is nothing but 200. 200 plus 1, which is nothing but 201. 201 is multiplied by K. And what is the value of K over here? K is nothing but this 16. Okay. Last point. In the output volume, dth depth slice is the result of performing a valid convolution of the dth filter over the input volume with a stride S and then offset it by dth bias. Now we can understand this with the help of this example. See, this is the output shape. What is the depth of the output? 2. 2 slices are there. This is the first slice 4 cross 4, and then this is the second slice 4 cross 4. First slice 4 cross 4 is the result of applying first filter on this input. Second slice is the result of applying second filter on this input. Third slice would be the result of applying third filter on the same input. Fourth slice would be the result of applying fourth filter on this input, like this. Now once again read that last statement. In the output volume, dth depth slice, it can be first depth slice, second depth slice, third depth slice, is the result of applying dth filter on the input and then offset it by dth bias. So this is nothing but the generalization of the convolution operation. Okay, so this was all about the convolutional neural networks. I hope that it is clear. Yeah, if you are having any query, then we can take some of the questions on CNN, and then we will continue the same in the next lecture, and we will touch some of the important healthcare stuff in tomorrow's session with the help of CNN.
Yes, sir. I am greatly thankful to Dr. Tausif Diwan, sir, for accepting our invitation and sharing insights of convolution neural network and deep learning. It's always truly be a pleasure to listen to you, sir. I hope your knowledge and perspective will definitely be fruitful for audience of this FDP. Thank you very much, sir. Now it's a time for Q&A. Participants, if you have any query, please.
I can suggest that, like, if you are interested in working in deep learning, etc., then you should first uh, implement some baseline CNN models. So you can see all these codes are ready-madely available here and there on some GitHub platform or on some other network platform also. So first of all, you should implement, and then once you implement these things, then it will be very easy to correlate the theory with the practicals of CNN.
Hello, sir.
Yeah, ma'am.
Sir, I have one question that why only 3 channels are used in a input?
No, ma'am, it depends on our input. It was just an example. We can take multiple channels also. It depends on the
Okay.
input shape. This was just
Somehow,
an example.
somewhere I read the thing there. 3 indicates the RGB.
RGB channels. Because if it is a colored input, then 3 channels are there.
And if it is a text, then
If it is a text, then it would be single one-dimensional array also.
okay. And how to decide how many filters we can apply in between the layers?
Ma'am, these are nothing but the hyperparameters. The
Okay.
one which I have told you, like weight and bias, these are nothing but the parameters.
Yes.
These things are completely dependent on the coder. For example, it is up to you. You can take 10 filters, you can take 20 filters, filter size 3x3, filter size 5x5. You can decide this filter size, you can decide number of filters, you can decide learning rate. All these are the hyperparameters.
Okay, but matlab how we decide if I want to develop any application, then how to
Yes.
decide?
So what we can do, ma'am, suppose we are taking an input of size 28. So we can start with 5x5 filter, and then we will see how it is performing.
Means we have to consider firstly ki how many filters we can apply there as
Yes.
matlab. Okay.
Just a minute, ma'am. I will give you an example. For example, see, we need to understand what is the nature of our input. Can you see this image?
Yes, sir.
Okay, so see here, this is nothing but the recognition of dog. What is the difference in the first, second, and third image that we need to figure it out? So you can see here, all these are dog images, but the amount of capture that dog is taking in first image is very high. Like 70% part is taken care by the by dog. In the last image, we can see only 10 to 20% of the total image is captured by the dog image. So if our application nature is of first category, then we should use larger size filter. But if our application nature is of third category, then we should use some smaller category or smaller size filter. So it depends on the application nature. First of all, we should understand our problem nature, and accordingly we should apply the filters.
Okay. Thank you, sir. You actually explain mathematical model very well. So thank you, thank you.
Participants, if you have any more query, I think it is over, sir.
Yes. Thank you, sir. Thank you, Khadeep sir, for inviting me for this session. Thank you, Razak sir.
Thank you very much, sir, for such an informative session. And participants, we will be having one more session by Tausif Diwan, sir, in the session yet to come. Sir, Professor Aicte sir is there. Nazish madam. With your permission, I am concluding today's session. Thank you very much, Tausif sir. Thank you very much, all the participants, for your patience listening. Thank you one and all.
Thank you, sir.